model. So how to generate a random network. Okay. So given the p value n and p, you can generate a random network. Okay. In the ER model, and we are looking at the inverse relationship between the clustering coefficient and node degree. Okay. So if you kind of find nodes of a certain degree and average out all the clustering coefficients, okay, so we can indicate that as C of k. So C of k is the average clustering coefficient of nodes with degree k. And if you plot the k versus C of k values for some real world networks, you get to see this inverse relationship. Okay. So that is basically as expected, because if a node has a larger degree, means like a node that you're looking at as a larger degree, so you cannot expect all its neighbors to be connected to each other. Okay. So if you determine the clustering coefficient, it's going to be a low value. Okay. So you may have some edges like this. Okay. So 1, 2, 3, 4. There are 8 neighbors. So you would expect to have 8 times 8 minus 1 over 2 edges at most, but you have only 3 edges between the neighbors, right? So the clustering coefficient for this node comes out to be this value, which is very small, right? So it is 3 over 28, okay? So it's close to 0.1.
So you are doing cluster coefficient.
Right. So on the other hand, if a node has a smaller degree, say for example just 3 neighbors, and if even one pair is connected, the clustering coefficient of this node is going to be 1 over 3. Okay. So if a node has smaller degree, you expect to have a larger clustering coefficient. So this is for the real world networks. But if you do a similar analysis for random networks, you would find the clustering coefficient to be not dependent on node degree. So it's going to be a horizontal line like this. So the clustering coefficient for nodes with different degree in a random network generated, say, with the ER model would be like this, a horizontal line, independent of node degree. Okay. Why? Because in a random network, the probability for a link between any 2 nodes is the same. So that's this p-link that you use to decide whether to set up a link between 2 nodes or not. Okay. So it doesn't matter how many neighbors you have. The probability for a link between any 2 neighbors is going to be the same. Okay. And clustering coefficient is a measure of probability of a link between any two neighbors of a node. So in a real world network, you don't have the same probability for a link between any 2 neighbors. But in a random network, yes, it's the same probability. Okay? Yes?
So with your denominator, that's n minus 1 divided by 2, right?
Yeah, the number of neighbors.
Okay.
Okay.
Because in other formulas, it was just the number of nodes total, right?
This is the local clustering coefficient. This is the formula. There's only one formula for that.
Okay. I just thought in the previous slide, the n minus 1 divided by 2 was n being the total number of nodes.
Oh, you mean that. It depends on which formula. So if you find local clustering coefficient, this is for a particular node. So there you count the number of neighbors of that node.
Okay.
Okay?
All right.
Okay, so what we are now going to do is try to quantify the extent of randomness in a network. Okay, so a network may not be purely like not random. Like there may be some edges that are randomly created. Okay, and some edges that may be due to the preferential attachment and so on. So we look at an index called randomness index that can be used to quantify the extent of randomness. Okay, so we'll go through this example. Okay, so by now you know, given a graph you can find what? The average degree of the vertices in the graph, okay, and get the degree distribution and so on, right? So from the average degree, we can also, and the number of nodes, we can also generate a random network that will have the same number of nodes as this node. This, say this is like a real world network, and this is like a random network that has the same number of nodes as the real world network, and average degree of the vertices here is also the same. Okay, so how to do that? So for this given network, you can find what? The degrees of the vertices, and using the degree values, you can find the average degree, right? So there are different ways you know how to find the average degree. One way is to just add up the degree values of all the vertices and divide by the number of vertices. The other is find the probability distribution and do what? Sigma kpk, right? So how you do that? Just count the number of nodes of a particular degree. So 2 nodes have degree 2, 3 nodes have degree 3, 1 node has degree 4, which node was that? 1, 2, 3, 4, node 5, and 1 node has degree 5, that is node 3. So you get the count of the number of nodes with a certain degree, and then divide that count by the total number of nodes. That will get you the probability pk for nodes with a certain degree. So then all you have to do is multiply 2 times 0.286 plus 3 times 0.48 plus 4 times this plus 5 times this. That's the weighted average, that's the average degree. So it will come out to be what? Let us do that here. 2, I'm just doing the summation of the degree values. So this 5, 8, 12, 14, 13, 22. So 22 divided by 7, so that is 3.14. Right? Yes. So 3.14 is average degree of this graph. So now how to generate a random network that has the same number of nodes and average degree close to this 3.14, or using this 3.14 as the average degree, how to generate the random network? Any answer? You've already seen how to do that last class. For a random network, what is the formula for the average degree in terms of the number of nodes and the probability for a link? If you have a node, what could be the maximum degree for that node of n in a graph of n vertices? N minus 1, right? And each of those n minus 1 edges to the neighbors could be there as a probability p link, right? So the average degree, so I denote average degree like what? Like this, okay? Equals n minus 1 times the p link, probability for a link between any 2 nodes. Okay, so in our case, we want to generate a random network that has the same average degree as the given real world network. So we know it's going to be 3.14, we expect it to be 3.14. And n is what? 7 vertices. So it's going to be n minus 1, 6 times p link. So using this, we can find what is the probability for a link between any 2 vertices. So this is like 0.524 that we used to work before. Okay. So you know how to now generate this random network, right? So for each pair, generate a random number, and if random number is less than or equal to 0.524, set up a link between the 2 vertices of that pair. The random number that you generate is greater than 0.524, there is no edge between the 2 vertices. So if I give an exam on this,
Sir,
each one.
please repeat that sentence.
Okay, so I understood up to P-link is 0.524. So now what you do? Let me go back to that. It's here. So write down all the pairs of vertices that could be possible in a graph of several vertices like this, starting from 0 to 6. And for each pair, generate a random number. And I showed in Excel how to do that. So if the random number that you generate is less than or equal to the P-link value 0.524, then there is an edge between the two vertices. Otherwise, there's no edge. So in this case, if this is a random number that get generated, this is what? Greater than 0.524. So there's no edge between 0 and 1 in my random network. Whereas if you have say 0.1721, it is less than 0.524, so there's an edge between 0 and 3. So that is how we decide whether to set up an edge between two vertices or not. So if I give an exam with this as a given network, each one should get ideally different random networks. Okay? So this is another way of finding whether we copied or not, right? Because if everyone writes the same two people write the same set of random number values, or the same set of edges, it's very unlikely that you got the same set of random numbers. Okay, so if you take home on this module, so be careful. So you have to run on your own. Okay. So once you get the random numbers, you can decide whether there's an edge between two vertices or not. All right. So is it clear? So once you get that, you can also find the degree distribution. So find the possible degree values. You may not even have the same degree values for these vertices, even though the average degree is expected to be the same for both the networks. You may not have the same distribution. So in this case, you also find 2, 3, 4, 5 as the possible degree values. Sometimes you may have a degree of 1, sometimes you may not have even a degree value, it may be 0, for some nodes may not have any neighbors and so on. Okay? Alright, so in this case it comes out to be one node has degree 2, one node has degree 3, 4 nodes have degree 4, and one node has degree 5. And you can also get the probability pk values like this. So now what we're going to do is we're going to find the clustering coefficient or local clustering coefficient of every node. So when we do that, we also kind of separate things based on degree. So the nodes of the degree 2 are what? 0 and 6 in this graph. So find the clustering coefficient for each node. For 0, node 0, what is the clustering coefficient of node 0? Yes, go ahead. What is the local clustering coefficient of node 0?
1.
Why? You have two neighbors. For 0, you have two neighbors, 1 and 3, and there's an edge between them. So it is 1 divided by 2 times 2 minus 1 over 2. So it is 1. Clear? If you have two neighbors, you expect 2 times, these are the maximum possible number of links. And the numerator is 1, there's one edge, and there is 1. Okay? Then node 6 also has degree 2 because we're looking at nodes with degree 2. And you have an edge between the two neighbors. So its local clustering coefficient is also 1. So now nodes with degree 3, 1, 2, and 4. So node 1 has 3 neighbors. So you have 3 times 3 minus 1 over 2 in the denominator. And how many neighbors are connected? Or how many pairs of neighbors are connected?
2.
0 and 3, 0, 2 and 3. So 0 and 3 are connected, 2 and 3 are connected, 0 and 2 are not connected. So it's going to be 2 divided by 3. Okay? Similarly, node 2 has 3 neighbors, 1, 3 and 5. How many pairs are connected? 1, 3 is connected, 3, 5 is connected, but 1, 5 is not connected. Okay, so again we have 2 over 3. So do this analysis like that, find the local clustering coefficient of each node. So then average out the local clustering coefficient for the individual degrees. So average of 1 and 1 is 1. And this is all 2 over 3, 2 over 3, which is 0.67. So the average of all these three is still 0.67. The average of just one number is by itself. So 3 over 6 is 0.5, 4 over 10 is 0.4. Okay. So if you kind of even visually look at this, you can observe even for a small network like this, as the degree increases, the average local clustering coefficient decreases, isn't it? So this is that pattern which I showed at the beginning of this class, where the clustering coefficient or local clustering coefficient, you can call either way, what? Decreases with degree. So the average, so C of k, now we understand what C of k means. So C of k means average local clustering coefficient of all nodes, say with degree 2. If you say C of 2, then C of 3, then C of 4, C of 5. So if you plot this k, this is the C of k, you could see this decreasing trend. Okay? Is it clear? Now, on the other hand, let's do the same analysis for this random network. Okay, so find the nodes with degree 2. There's one node with degree 2 which is 0. There's another node, there's one node with degree 3 which is node 2. And 4 nodes with degree 4, so 1, 3, 5, 6 and so on. So find the local clustering coefficient of each of them. So node 0 has 2 neighbors, 3 and 6, but there's no edge between them. So the clustering coefficient of node 0 is 0. Okay? Then node 3 has, node 2 has 3 neighbors. Then, so 1, 6 and 4 are 3 neighbors. 1 and 4 are connected, 4 and 6 are connected, but 1 and 6 don't have an edge. So it's going to be 2 over 3.
Sir, how we are preparing the random network?
I went through the random numbers.
Yeah.
Then take a random number for each pair, and if it's less than or equal to the p-link value, there's an edge between the vertices, the pair, or otherwise there's no edge between them. Okay?
Between the pair?
Between the vertices, that pair. So for a pair 0, 1, generate a random number. It comes out to be greater than 0.524. So there's no edge between 0 and 1. Whereas 0 and 3, this is random number that I got. So this is less than 0.524.
Yeah.
So there is an edge between 0 and 3.
Okay.
Okay?
We need to find each.
Generate random numbers like this. So open an Excel spreadsheet and generate random numbers. Write down all pairs, generate random numbers, and decide which pair has an edge between them, between the two vertices of the pair and not. Okay? Alright, so now if you take the average of this local clustering coefficient values, so if there's only one value, it's just the average. Okay? Now the average of these, so here we have different clustering coefficient values, so we take the average of these 4 values, you get 0.542 and then 0.6. So here, even though this is like an outlier case, the 0, the other 3 values are pretty close to each other, 0.67, 0.542 and 0.6. So you see that even though the degree increases, the local clustering coefficient, the average, C of k, remains more or less the same. So if you tend to plot this, it is going to come like almost like a horizontal line. This is a small graph, so you cannot really expect to get a real horizontal line, but the values are very close to each other. So this is what we want to quantify. Okay, to what extent we could, so this is expected of a random network, right? So, and this is expected of a real world network. But in some cases, you do not observe something like this. It could be like this, or it could be like this. So we want to study networks on this basis and quantify. Okay, so let us do some analysis. So last time I showed in Excel, I'm not sure I showed how to find fit a line. You all know how to fit a line in Excel? Fit a straight line. What's the equation of a straight line?
Y equal to mx.
Okay. So y equals like slope times x. So plus what? Yes. So we are interested here in the slope. Let me maybe have this. Okay, so the degree okay, so all you have to do is try to fit this to a straight line. So go to straight line. Okay. Chart, and you can choose this. Yeah, straight line is better, so let us do it. Chart, there's a straight line option here. Okay. So now try to right click and find add a trend line. Okay, so click on add trend line, and you want to choose the linear option there, and so display equation on chart and display R square value. Okay, so R square is a measure of how good is the fit. Okay, and just close this. So this is the equation. Okay, so we expect to see a decline like this, but it's close enough to this. Okay, so R square is like 0.9344. So if it's closer to 1, it's really a good fit. Okay. Now the slope here. So this is the slope, negative 0.197. Okay. It's a negative slope because it's a declining trend. Okay. So the randomness index is basically the R square value denoted with the sign of the slope. So it's a negative slope, and R square is this. So the R square, the randomness index for this network is going to be negative. Okay. Now we have to take the square root of the R square value. So square root of the R square value here is 0.9667. So the negative sign is corresponding to the slope of the sign of the slope, which is also negative, right? So this negative sign accounted for this negative sign here, and the square root of the R square value. So that is a randomness index. So the randomness index will range from -1 to 1. Why -1 to 1? Because R square will also range from 0 to 1, because it's R square. But if you take a square root of it, it could be -1 to 1. So it's -1 or +1 or negative or positive depending on the slope. So if the slope is a decreasing trend like this, it's a negative slope. So it's negative value for square root. Is that clear? Now on the other hand, if you try to plot the degree versus average LCC values for the random network, right? So if you try to do that here, highlight and insert chart line. Okay. Let's see. I think we could even discard. Okay, you could have this. Okay. So now try to add trend line. Display equation on chart, display R square. So this is how the other data is getting fitted. Okay. So the slope here is a positive slope. Okay, because this looks like an increasing trend. And the R square is 0.496. So if you take the square root of that, it will turn out to be 0.7043. And you put a plus sign, positive sign, because it is an increasing trend. Okay? So the randomness index of this random network is this. So the general trend is the randomness index will range from -1 to 1. If it is positive, that's an indication that network is more random in nature. If it is negative, then it's an indication that the edges are not random. They are created due to some preferential attachment or some reason and not random. So again, what random means, like if I have a network of 10 people like this, if I just say, okay, you all talk to each other for say some time, okay, and then I come back and I ask who talked to who, right? So, and then based on that, I start to build up a network, okay? So when I went out and you all decided who to talk to, you just chose people in random, right? Then the network I could expect to get could be something like this. They're clear, okay? On the other hand, if you prefer to talk to someone, go and talk to some preferred person. So like this, node 3 is a preferred person, so out of 6 vertices, 5 of them talk to node 3. Whereas nodes 0 and 6, only 2 people talk to them. So that is typically expected in a real world network. You have some preference for people to talk to each other or for edges between 2 nodes. Okay? So that's the kind of similarity. Is that clear? So for a random real world network, you expect to have a negative randomness index. So the more it's closer to -1, the less random the network is. And more positive and closer to 1, the more random the network is. Okay, so this could be used as a quantitative measure of assessing the extent of randomness in a network. Okay?
More randomness means?
More positive, closer to 1. Less random means closer to -1.
It's not random, right?
Which one?
This one, the first
This one is not random, so that is why you get -0.96 or something. It's almost not random at all. So if you get -1, that's the best you could get for a real world network. It's not random at all. Okay. And if you get close to +1, like this, because as I said, if the network is random, the relationship that you expect between the degree and the C of k, the average clustering coefficient of the degree, is going to be a horizontal line like this. And that will correspond to actually what value? What is the corresponding value here? The C of k. C of k is like what? The clustering coefficient, right? It will range from 0 to 1, because it's a ratio of the actual number of edges divided by the maximum possible number of edges. So that ratio will be always from 0 to 1. And this value is the P link, because it's just the probability for a link between any 2 vertices, right? So that is this horizontal value here. So this is what you expect. Now, as you can see in this example, some random network cases, you could even see it's almost like a horizontal line here. But because of this outlier case, Excel tried to include that in the fit. So that is why it comes out to be like an increasing trend. But if you discard this point, it's more or less like a horizontal line. Okay? And you get something like this because of being a small graph. If you work with larger number of nodes, you don't expect to get some outliers. So you can try to get a horizontal line like this. Okay? Clear? So try, if you are good in programming, you can just generate a random network of say 100 vertices with certain probability for a link between any two vertices, and try to find the distribution of k versus c of k and see how it comes out like. Okay? Something easy to do. That is how you develop your programming experience. Okay? Alright, so some more math problems. So consider a random network generated according to G and P means graph with a certain number of vertices and P link probability P. So that's the ER model. And total number of nodes is 12, so N is 12 and P link P is 0.2. So just to review everything about random networks. So find the average number of links. So how to find the average number of links with this given information? Yes? So given what? The number of vertices, nodes is 12, and the probability for a link between any two nodes, P link or P is given as 0.2. So with these two information, you need to find all this average number of links in the network. Any idea?
N times n minus 1 divided by 2.
That is the n times n minus 1 over 2 is the maximum possible number of links.
Maximum.
And each of them could exist with a certain probability. Like we did n minus 1 times P link for average degree. Same idea for average number of links. So this is the maximum possible number of links.
Oh.
And each link could exist with a probability P link. So that is going to be the average number of links in the network. Is that clear? The average node degree, as I just said, that's going to be n minus 1 times P link. Okay? Now what is the standard deviation of node degree? Square root of average degree. Okay, so the average degree will come out to be 11 times 0.2, so it's 2.2. So that's the average degree. And why square root of average degree? For a random network, okay, or this is a Poisson distribution. So for a Poisson distribution, the average, the standard deviation is square root of average degree. Remember this one? So standard deviation is a measure of how much the degree values are deviating from the mean, the average. So for a Poisson distribution, which is what we see in this random network ER model for the node degree, the standard deviation of node degree is square root of the average degree. So once you find the average, the standard deviation is going to be square root of the average degree. So it's going to be square root of 2.2. Okay? Then what else? The average path length, or the distance between any two nodes. How to find the average path length? Okay, we don't use this formula yet. Might have mentioned before. Okay, so the average path length for a random network would be given by this formula. There's a derivation for this, we are not seeing that. So log of n divided by log of average degree. So that is the average path length between any two nodes in a random network of n vertices and P link value. Of course, why? Because we got average degree based on the P link. So given the number of nodes and P link, you can find the average path length. Okay. Now I think I might have mentioned before, if the average path length is proportional to log n, what can we call that network as? The network is said to exhibit what is called the small world property. So think about this. If your network has n vertices, but the average path length between any two vertices is log n. You know, log n is much smaller than n. So if n is even like million, log of a million is going to be a very small number, 10, 12, and so on. So that's one. Then such a network is said to exhibit what is called a small world property. So small world means you can reach between any two nodes within 10 edges. Okay, or the path length. That's what it is. Okay. So random networks also exhibit small world property because according to this formula, the average path length is log n divided by log average degree. So because of this, random networks generated according to the ER model are considered to exhibit small world property. Okay. Now the average local clustering coefficient for any node is going to be, because we don't even have a network, so we cannot find the average local clustering coefficient using our regular approach. What is our regular approach? Actual number of edges divided by the max number of edges. But this is a random network, so we should be able to say the local clustering coefficient for any node is expected to be what? That p-link value, because that's the probability for an edge between any two nodes. So that's a 0.2. Okay. Then I may do a twist and ask you, what is the expected local clustering coefficient of for a node with exactly 5 neighbors? Okay. So you may wonder, where is the graph and how can I find a node that has exactly 5 neighbors? Isn't it? But again, the answer for this is going to be what? Is again p-link. It doesn't matter how many neighbors you have, 5 neighbors or 10 neighbors, you're going to have your expected local clustering coefficient is same as p-link. Okay, so it's also 0.2. Is that clear? So given a problem like this, you should be able to answer. Okay. Now, so because of this distribution and certain other things that we also saw, real world networks are not really random, because for a real world network, the K versus C of K distribution is like a decreasing trend like this, whereas for random network, you expect to have a horizontal line like this. Okay. So real world networks are not really mimicking the properties of random networks. Why we need to study about random networks? Okay. So one thing is like this randomness index analysis that we just did. We want to quantify the extent to which a real world network could be random in nature. Okay. So if you find, say, the randomness index of a network, of a real world network, and it comes out to be positive, like what we got. Okay. We got a negative value, but let us say unlike some, if this was a real world network given to you, if this was the real world network given to you, right? If you find the randomness index of this real world network, you would get a positive randomness index, right? Then we cannot say it is non-random in nature, because if the randomness index is positive, it means what? The K values, either a horizontal line or the increase like this, isn't it? So such a real world network is considered to exhibit some randomness among the edges. Okay. So if you get a positive randomness index, then it's an indication that the network exhibits random properties of a random network. So then we can focus our study on those lines. On the other hand, if I give you a real world network like this, and you get the randomness index to be close to -1, then it's a clear indication that there's very less randomness in the edges, among the edges. And if it's more closer to -1, we can also say there's a preferential attachment, because if there was some randomness, it would not be that close to -1. It will be some moderate value. Okay, so then we can focus our analysis accordingly, so that we can study this network for some preferential attachment. That's what we're going to see now. Okay, to see if nodes really prefer to attach to some vertices or not. Okay, so that is one reason why we study random networks, to decide whether a real world network could exhibit the properties of a random network. Okay, so that's like a starting point or a benchmark. So if you see if there's anything common, the degree distribution of random networks is Poisson in nature, like the curve we just showed. Whereas real world networks are not that Poisson. Okay, so if you plot the degree distribution of real world networks, they do not exhibit a Poisson distribution. Okay. Now, in terms of the connectedness, okay, so real world networks, if you just find for real world networks, even if the average degree is less than log n, you still expect the whole network to be connected, and we say one single giant component. A giant component is nothing but all the vertices are in one component, reachable from each other. Okay, so but the vertices may have a small degree. Okay, and some vertices have a larger degree, but still they are reachable to each other and they are in one component. So that's called the giant component. And you can see a giant component for real world networks even if the average degree is less than log n. On the other hand, for random networks, so again we could more mathematically study this, we are not studying this here, but for a random network, in order to expect a giant component with all the vertices part of it, the average degree has to be greater than log n. So there's a fundamental difference. So it takes more edges in a random network.
So what is log n?
What is log n? Logarithm of n.
Yeah, no.
N is the number of nodes. Okay, so the average degree is expected to be greater than log n in order to see all vertices in a giant component in a random network. Okay, so that's a fundamental difference in the connectedness. Okay, between the two. The average path length, yes, both exhibit the same small hole property. So several real world networks also, the average path length is proportional to logarithm of n, and for random network also it is logarithm of n. Because in terms of clustering coefficient, they have different relationship, right? For a real world network, you would expect to see a declining trend for k, which is c of k, whereas a random network, you see a horizontal line. So other than path length, they do not have any similarity between them. Okay, right? So these are something you need to know. Okay, so we're done with the random network model. So let us now move on to scale-free network. Okay, so scale-free network is kind of the model type of network where you see some preferential attachment. Okay, so some nodes are preferred for attachment to other nodes and so on. Okay, so like a random network follows a Poisson distribution for the node degree. Scale-free network follows a power law distribution. So power law distribution is something like this. If you plot the k versus p of k, for a random network we saw that we got the Poisson curve, right? So for a random network we got something like this. So this is characteristic of random network, a Poisson distribution. Whereas this is called the power law distribution. You might have come across this name called Pareto distribution. They come across this name, Pareto distribution. So they are all the same. It's also more commonly called the heavy tail or long tail distribution. So why it's called heavy tail? Because in a Poisson distribution, so this is average degree, right? So after a certain values of degree, the probability is very close to zero. The probability of finding a node with a certain degree is close to zero. Whereas here, it's a long tail because even though the average might be somewhere here, okay? Again, you look at the nature. There's a high probability for nodes with a smaller degree, and right here, quickly, the probability for a certain degree decreases. But it decreases, but it doesn't go to zero. So it keeps on having a non-zero probability. So you could even have a very large degree value, and the probability of finding a node with that large degree is still non-zero. So this is characteristic of like what? The airport network. In an airport network, you could have a hub node with a very large degree, right? Whereas there are a lot of airport network, majority of the nodes have small degree because most of the airports are in the smaller cities. But there are some few cities that are like a hub, right? So the degree distribution for an airport network will appear like this. Okay. So that is characteristic of a heavy tail distribution. Now we saw an equation or a model that can be used to fit the Poisson distribution, right? What was that? Remember? P of k equals e to the power minus average degree rise to k divided by k factorial. Right? So this was using the k values, you can generate the P of k value, using k and the average degree. So if you know the average degree expected in a random network, for different k values, you can generate the P of k values. We saw that previously. So now we are going to see how to generate the P of k values using the scale-free network model. Okay, so the scale-free network model is this. The probability of finding a node with a certain degree k is proportional to k raised to negative gamma. So this gamma is like a constant, is a degree exponent. That's the name of the gamma. Okay, and it is typically greater than 1. We'll see later why can't it be less than 1. Okay, so gamma is greater than 1. So if you remove this proportionality sign, you can introduce a constant, like the proportionality constant. So P of k is C times k raised to negative gamma. So this is the equation for a power law distribution, okay, or for a scale-free network model. So let us analyze more this model. So the first thing is, let us say we want to find what could be the value of this proportionality constant, okay, for a given gamma. So if your gamma is known, okay, we can find a value for this proportionality constant. How? Just some fundamentals of probability. The sum of all the probability values should be what?
1.
1. So the sum of, for all possible values of k, the sum of all the P of k values should be 1. Right? There's some fundamentals of probability. So the k value could go from 1 to infinity. Right? At least theoretically infinity. Okay? The degree values. So let us substitute. What is P of k? C times k raised to negative gamma is 1. The C is a constant. So the C can be brought outside and written as C times k equals 1 to infinity, k raised to negative gamma is 1. So if you bring it the other side, that is the formula for C. 1 over sigma k equals 1 to infinity, k raised to negative gamma. Is that clear? Okay? So this is this summation, there is a name for this. You don't have to remember this name, but again, it's called the Riemann zeta function. Okay? So if you denote it like this, we can say this is 1 over that symbol gamma. Okay? I forgot what to call that symbol. That's the way you can call it. There's a name for each of those symbols, right? Like gamma, beta, and all.
Zeta?
Zeta? Okay,
Zeta.
zeta of gamma.
I don't know, I'm just scaring that.
Maybe.
That's the name of it. It's Zeta, if I'm not mistaken.
Zeta.
Uh,
Okay, all right. Okay, so you may wonder how to, because it goes up to infinity, right? So any idea how can we find in reality for a given gamma the value of C? Open an Excel spreadsheet, okay? Try K values 1, 2, 3 up to some number, say 10 or 20, okay? Find, because again you are given what? Gamma. So let's say gamma is 2.5, okay? So then find K raised to negative 2.5, okay? So find all the values. So that is K raised to negative 2.5. Now you see it's a negative exponent, right? So as K increases, if you have 100 raised to negative 2.5 is going to be a small number. So as you increase the K, the contribution of K raised to negative gamma will lower to the sum, okay, will decrease. So after a while, you don't even need to consider those K values. So you can stop when K raised to gamma becomes very negligible. And then you add up all those values. So that is your proportionality constant. Okay? So I have shown this up here. So it's nothing complicated. So what I just said is shown here. Okay? So starting with gamma values of 1.9, I generate the K raised to negative gamma values for different values of K, say from 1 to 20. And I add all of them. So the sum comes out to be say 1.676. So I stop when K raised to negative gamma is like 0.003, like 2 decimals of 0. So the sum comes out to be 1.676. And what is the proportionality constant? The inverse of the sum, 1 divided by the summation. So the inverse of 1 divided by 1.676 is going to be 0.596. So that is the value for the constant, proportionality constant, in a theoretical power law model. Okay? So try different values of gamma. Okay? So the larger the gamma, the higher the value for the proportionality constant. The lower the sum, of course. So because if you increase gamma, it's like K raised to negative gamma. So the scores, the K raised to negative gamma values are going to decrease. So summation is going to be getting smaller, and the inverse of the summation will get larger. Okay, so that is something you can figure out, right? So given a gamma value, you can find the proportionality constant. So that is what you need to know. How? Using this summation. K equals 1 to infinity, K raised to negative gamma. Okay? So now, we can do some more theoretical analysis here. So once we know the C values, the proportionality constant values, for a given gamma again, so for a given gamma, say gamma is 2, we can find its proportionality constant. We just saw how to do that. So once we know the proportionality constant and the gamma value, we can generate the K versus P of K distribution, right? Because the formula for P of K is simply C times K raised to negative gamma. We know what C is, we know what gamma is. So for different values of K, we can find P of K, right? So we can now even plot K versus P of K. So let me show one thing right away so that you can, so it's here. So if you plot here, for example, gamma is 2 and gamma is 3, okay? The K versus P of K distribution. You get the typical power law pattern, okay? So if you pay close observation to what happens to the P of K values for larger K, so 2 different values of gamma, you can see if gamma is 2, P of K is 2 zeros, 0.00, then 157. Whereas if gamma is 3, it is 0.30, 00010. So essentially what happens? for a larger gamma, the probability of finding a node with a larger degree is less, right? So because if k is 20, that's a degree, the probability of finding a node with larger degree is like lower compared to this case, right? If you look, just look at the numbers. So this is the probability of finding a node with degree 20 if gamma is 3, and this is the probability for finding a node with degree 20 if gamma is 2. So that means there's a high probability of finding a node with degree 20 if gamma is lower compared to the higher values. Okay? So if you look at again, so that is this side, the tail side. Whereas here, gamma is 3 is the red line and gamma is 2 is the blue one. So if gamma is 3, there's a high probability for finding nodes with lower degree compared to gamma being 2. So if you put both together, so if gamma is 3, there's a high probability for finding nodes with a smaller degree and low probability for finding nodes with a larger degree. So that means there's not much variation in the node degree. Most of the nodes are going to have on the lower side of the degree. There's a very low probability of finding nodes with a larger degree. So which means what? On the other hand, if gamma is 2, then you have relatively low chances of finding nodes with a smaller degree. Of course, majority of the nodes have smaller degrees still, whereas there's a reasonably high probability of finding nodes with a larger degree. So now consider a hub node. So in a scale-free network model, you are more likely to find hub node for lower or higher values of gamma. Hub means what? Nodes with a larger degree. So the chances of finding a hub node is high if you have a lower gamma value or a higher gamma value. Lower, right? Because according to this, if gamma is 2, the probability of finding a node with degree 20, that's like a hub node, is going to be larger than the case with gamma being 3, right? So that's why I state here, for larger values of the degree exponent gamma, the chances of observing a hub with a larger degree decreases. Okay? Is that clear? So you should understand the how gamma plays a role in designing a scale-free network. So if gamma is high, the network is not going to be as scale-free as network with lower values of gamma, the degree exponent. Okay? So we could even later see that as gamma gets larger, the network starts exhibiting characteristics of even a random network. Okay, so if gamma is larger, because most of the nodes have similar degree, comparable degree. Okay. Now there is a relationship between. So one case why gamma has to be say greater than 1 or greater than 2. It's more preferably greater than 2 for all practical purposes, and even for this math relationship that we're going to see. So we can even derive this, but we're not deriving that. So in a scale-free network model, the relationship between the maximum degree for any node and the minimum degree for any node is given by this. So K max is K min times n raised to 1 over gamma minus 1. So with that relationship, let's try to analyze what happens or what are the possible values of gamma that can make sense. Okay. So let us say n is given, fixed, so 100 nodes. So if n is 100, and let us plug in a value for gamma, okay, so different values of gamma. And let us assume for simplicity k min is 1, okay, so minimum degree for any node is 1. So k max simply comes out to be n raised to 1 over gamma minus 1. So n is also given, so 100. So for different values of gamma, we can generate the k max values. Okay? So if gamma is 1.5, this is going to be like what? 1.5, 1 over 1.5 minus 1. So that is like 100 raised to 1 over 0.5. which is like what, 100 square.
Mhm.
So it is like 10,000. Now what does it mean? You have only 100 nodes, but you are getting K max to be 10,000. Is that practically possible?
Mhm.
You have only 100 nodes, so the maximum degree you can expect to have is 100 minus 1, 99,
Yeah.
right? So you cannot have a node with K max 10,000. So this is why gamma cannot be like in certain range, even 1.5 or even lower. If it's even less than 1.5, K max will be a very large value. Does not make sense. So if gamma is 2, what happens? This is going to be 1 over 2 minus 1, which is going to be 1 over 1 in the here, so it's 100. So again, you expect to see 99 to be more precise, right? So even gamma is 2 is not that acceptable. You expect gamma to be greater than 2. Okay? So if gamma is say 2.5, so that's going to be 1 over 2.5 minus 1, so this is going to be 1 over 1.5. And that comes out to be 21.5. 100 raised to 1 over 1.5 is 21.55. And it starts to make sense. You have 100 nodes, and the maximum degree that you expect is 21.5. Okay, mathematically. Then as you increase gamma, you observe what? K max to decrease. And this is again consistent with this relationship. So as you increase gamma, K max is what? Corresponding to hub node because it has the largest degree. So the maximum possible degree you can expect in a network of 100 nodes when gamma is 3.5 is 6.31. So instead of like 100 or 99, you are now expecting only 6 as the maximum degree for any node in a scale-free network of gamma being 3.5. So we can start seeing, so if minimum is still 1, right? So the degree values are between 1 and 6 if gamma is 3.5. So that is more or less characteristic of a random network. The degree values are close to each other. Okay? Any questions so far? Okay. So once we can generate the K versus P of K distribution like this, we can go ahead and also find the average degree, okay, expected for a given gamma. Okay, so again, all these are theoretical analysis. Later we'll do some problems for some real world scenarios. So how to find the average degree? Just do KPK, summation of KPK. So you have the K values for a given gamma and the constant, the proportionally constant based on the gamma. We can find the PK values using this relationship. So now just do K times P of K and add them up. So that is the average degree. So again, what you can observe, as gamma increases, the average degree decreases. Okay. Now, in addition to average degree, we can also find some other statistical measures. Height of this kurtosis, these are standard deviation. Okay. So standard deviation itself is like a measure of how different or how deviating or the degree values from the mean. So mean is the average, right? So if all the nodes have the same degree, what will be the standard deviation of that network? If all nodes are the same degree?
0.
Zero, there's no variation, right? And also there's a name for such a network. If all nodes have the same degree, it's called a regular network. Okay? So the standard deviation is a measure of how deviating or the degree values from the average. And that is in your statistics class, you might have studied the second moment, third moment, fourth moment, and so on. Have you studied that? Okay. It's nothing but, you see here, this is the formula for standard deviation. The K minus the average degree square. Sum all those different squares. And then divide the summation of all the squares of the differences by n. And take a square root of that. That's the formula for standard deviation. Okay. Now, this is one way to find, this is one formula to find standard deviation. The other way to find standard deviation, the average degree, what was the formula? K times Pk, right? Summation of K times Pk is the formula for average. Now, the standard deviation can be also found using this formula. So P of K times K minus the average square. Okay, the P of K times K minus the average square. So this is the second, the exponent is 2. Now there's something called kurtosis, where in the formula P of K times K minus average, the exponent is 4. So it's the fourth moment they call it, okay? So the kurtosis is another way to analyze the variation in degree, okay? And the specific purpose of kurtosis is this: how heavy tail the distribution is. You know, the scale-free networks, I said, have a heavy tail distribution, that the tail goes on for a large value, right? So we can kind of quantify the extent of scale-freeness, the heavy tail nature of this network, by determining the kurtosis. So if the kurtosis of a network is high, typically above 3, then we could say the network is scale-free nature, like randomness index. So if the randomness index is like close to close to positive 1, we say the network is more random, right? So like this, if the kurtosis of the degree distribution is above 3, then we can say the network is exhibiting scale-free properties or scale-free nature, okay? Is that clear so far? Okay, so find the kurtosis based on the degree distribution. We'll see an example soon. And if it's above 3, then we can say it's more scale-free nature. Okay. Then sometime back, I also mentioned why we call these networks as scale-free. In a random network case, the standard deviation of node degree was what? What's the formula we just saw earlier? Square root of the average degree, right? Okay, so standard deviation is expected to be less than the average. So I said most of the degree values of the nodes will be in this range, right? So this is your average and this is your standard deviation. So we say the degree values are in the range, the average plus or minus standard deviation, right? So this is like a scale for the degree values. Whereas for a scale-free network that exhibits this power law pattern like this, for K versus P of K, the average degree might turn out to be something like this. So this is the average degree, okay? Whereas you see here, even though the average is a very small value, like we saw 1.5, 2.5 and so on, there could still exist a node with a very large degree, say 200 and so on, right? So we cannot attribute a scale like this, because again, a Poisson distribution, what did I say? For reasonably larger values farther from the average, the probability of finding the node with that degree is close to 0, P of K is close to 0. Whereas here, it's a non-zero probability. So we cannot say the degree or the range of degree values for nodes in a scale-free network is average plus or minus standard deviation. There's no scale possible. And if you find the standard deviation of scale-free networks, as we'll do soon, the standard deviation can be even larger than the average, especially if gamma is smaller. For lower values of gamma, what did we say? The chances of finding a hub node is high, right? So the chances of finding a hub node is high means like there exists a non-zero probability for even larger values of K, right? the standard deviation could even come out to be larger than the average. So it doesn't make sense to say that if standard deviation is above average, so for example, if average is 10 and standard deviation is 20, does it make sense to say the range of degree values is 10 plus or minus 20? No, because it means like what? The degree values could be like negative 10 to 30. Can you have negative degree values? Does it make sense? So it makes sense to say like this only if standard deviation is going to be less than average and typically low compared to average. Then only you can say it is average plus or minus standard deviation, like the range. So if standard deviation can be above average, we cannot have a scale, right? So that is why typically if gamma is less than 3, and you saw it cannot be less than 2 for all for the number of nodes, right? For the maximum degree. So between 2 and 3 is for gamma is the commonly considered range for scale-free networks. Okay, where standard deviation is above average or expected to be above average. Okay, so that is why we call this network as scale-free. We cannot assign a scale for the degree values for the vertices. And if gamma becomes greater than 3, you can see the standard deviation becomes less than the average. And that's another reason why we consider as gamma increases, the scale-free networks start exhibiting the characteristics of a random network. Because for a random network, you can see standard deviation less than average, and you can start seeing a scale. So like that, if as gamma increases, standard deviation reduces, because again, as you saw, the range for the degree values reduces, so k min to k max, right? So more or less, the nodes have more or less the same degree or comparable degree. So the standard deviation getting lower, closer to 0. And average will stay there. So we can start seeing the characteristics of random networks if gamma gets high. Okay, clear? So I think we have, okay, we can stop here. So